Namaste. Welcome to this channel, Chemistry Made Easy by Dr. Ashok. We are discussing Ahrland, Chatt and Davis classification. So this is the part of theories of acids and bases. Ahrland, Chatt and Davis has classified the Lewis acids and bases on the basis of their energy, their electron shells, means their outer sphere of electron shells. When the electron shells are compact and when the electron shells are loosely bound, or there is possibility of polarization or presence of the electrons, then their nature is different. So on this basis they classified these metal ions into two groups, and the first is class A metal ions, class A metal ions, and second is class B metal ions. So, on this basis, class A metal ions are those which are present in alkali group, that is S block of the periodic table. So, these are metals from S block and some metals from B block with higher oxidation states. So he classified the metal ions which are having nature like this. That is metals from S block. And what are these? These are alkali metals. Alkali metals. Alkaline earth metals. Alkaline earth metals. And transition metals with higher oxidation state, such as we can consider metal ions in higher oxidation states. For example, if we say scandium, these are, say, scandium in 3+, or if it is possible, other metal ions. For example, if we say Fe3+, or we can see at Mn any higher oxidation state, such as +2, +3, +4, +5, +7, etc., or any other oxidation states, cobalt 3+. So in this way, because of this, these metals are showing greater power to polarize the anions. So because of this nature, they are smaller in size. They are small in size, have greater polarizing power. They have such strong power to polarize the anions. They do not have d electrons, or the d electrons are very few. So such metal ions are called class A metal ions. You know the alkali metals such as Na+, K+, etc. Similarly, the alkaline earth metals Mg2 plus, or you can say Ca2 plus, etc. So in this way, if we consider the transition series, first half of the transition series, these are mainly class A metal ions, and later transition series elements are remaining, that is class B metal ions. Then we will see what are class B metal ions. Class B metal ions. So these are metal ions from transition metals. These are transition metals, of which are present on right side of the series, present at right side of transition series. They have d electrons available. They have d electrons available. So these are the metals. These are the metal ions which are having the lateral transition elements. They have lateral transition elements such as, we can say, copper, platinum, palladium, silver, gold, copper, cobalt, etc., which are in lower oxidation state as well as higher oxidation states. So they are having less polarizing power because they are relatively larger in size. So they are large in size, less polarizing power. They have larger size and less or smaller polarizing power. So these are heavier, we can say heavier transition metal ions. They have also capability to form pi bonding, in contrast to class A metal ions, which do not show formation of such pi bonds. Then if we see the class B metal ions, they are having low oxidation states, or they can show even zero oxidation state and can form complexes. If we see the formation of complexes, it shows that the class A metal ions can form complexes or any stable molecule with, we can say, the Lewis basis. Class A, we are considering class A now. Class A metal ions form stable compounds or complexes using the ligands, or we can say Lewis basis, in which the donor atom is the atom like nitrogen and nitrogen, oxygen, fluorine, chlorine, etc. And the class B metal ions will form stable complexes with ligands or Lewis bases, which are having the heavier elements of these groups of oxygen, nitrogen and fluorine, that is heavier elements, that is sulfur, selenium, and in case of halides we can consider the bromine, iodine, etc. So heavier metal ions, heavier non-metal ions will form complexes with the metal ions with the class B type of metal ions. and class A type of metal ions will form complexes or stable compounds with ligands having donor atoms such as nitrogen, oxygen and fluorine. Now if we see the solubility, if we see the solubility of these compounds, for example, if we see solubility, so if we see their salts of these A group, so they have solubility, these are F minus, Cl minus, Br minus and I minus. So chlorides of these class A metal ions are more soluble than chlorides of class A metal ions, than bromides of class B metal ions, than halides of class B metal ions. So this order is same here, but here these are more soluble. These are more soluble in water. Whereas class B metal ions also show the same order, that is F minus, Cl minus, Br minus and I minus, but they are less soluble. Their solubility is less. So in this way we can consider the solubility order. So class B metal ions shows the same order, but their strength or formation of these compounds is different. Class B metal ions have large enthalpy of reaction with phosphorus donors. So as I have said earlier, that if we consider the complexes of ligands containing nitrogen, and if we compare the complexes of various metal ions with their ligands containing phosphorus, and it shows that the nitrogen containing donor atoms, nitrogen containing ligands are strongly donor or powerful donor atoms, means Lewis bases, which are forming more stable complexes with class A type of metal ions. But if we consider the phosphorus containing donor molecules, or the again lower such as sulfur or selenium, tellurium, etc., then these are forming stable complexes with metal ions of class B group. So here Ahrland, Chatt and Davies explained the class B metal ions as powerful, means these class B metal ions have d electrons available. We have seen earlier that these metal ions have d electrons which are easily available for formation of pi bond with ligands, and therefore these are giving different types of solubilities and the energies which are associated, that is called enthalpies of reaction. If we consider the metal ions such as Tl3 plus and Tl plus 1, so in this case the d electrons are not shielded. The electrons are not shielded by s electrons, means 6s electrons are usually here, means they are lost, and therefore the 6s electrons are not available for screening the d electrons. So d electrons can be easily made available. So these are we can see in this case we can say 6s electrons are screening nuclear charge on 5d electrons, and therefore in this case the 5d electrons are easily available for formation of pi bonds. But in this case the d electrons are not that much easily available for formation of pi bonds. So here the vacant d orbitals here are suitable for formation of pi bonds and pi antibonding molecular orbitals. Then if we see the Pearson's concept, if we see Pearson's concept, it shows that the hard Lewis acid forms more stable complex with hard Lewis base, means it prefers to form hard combination. So it prefers, means hard Lewis acid prefers to bind with hard Lewis base and gives stable complex. For example, you can see H plus and F minus gives a stable complex because both are hard species. Similarly, if we consider these other species like cesium plus and I minus, these are soft species and therefore they can also form stable structure. And if we see the compound like this H plus and I minus, then here it is, you will find that this is hard soft combination and therefore it is not stable, but these are stable structures. These are stable combinations because there is hard and there it is soft. So Pearson, according to Pearson, the hard combination of Lewis acid and Lewis base or soft combination between Lewis acid and Lewis base will give stable molecules or complexes. But if the complex is formed with any of the hard species with another soft species, means one hard and one soft, combination will not give a stable structure. For example, if we consider the hardness, so Pearson's concept is like this. Now, if we consider the hardness parameter F minus, Cl minus, Br minus and I minus. So here this is most harder and this is soft species. So hardness decrease in this order, or we can say softness increase in this order. Then we have to consider that what is meant by the hardness or softness. So in order to explain this, we will take the example of many examples such as Ag plus. And if we see the soft species or hard species, we can consider all these. H plus I minus gives HI. Gives HI, AGI, AGI. AGI. So this AGI solid is stable. Why it is stable? Because Ag plus, this is soft species. This is soft, this is soft. So this is soft combination, and therefore it is stable. Similarly, if we take another example, that lithium Li plus F minus, so it gives Li F solid. So here lithium is hard species, this is also hard, so there is hard combination, and therefore it is stable. Means the bond between the Lewis acid and Lewis base is stronger, and therefore this combination is favorable. Whereas if we consider the lithium plus Br minus, this combination is not favorable. This combination Li plus I minus is also not favorable. But in case of, if we use metal ion of class B, then I minus and Ag plus combination is favorable. Ag plus Br minus combination is favorable. But Ag plus and F minus, this combination, or Ag plus and Cl minus combination is not much favorable. So this is because of the hardness. So hardness depends upon, so it can be considered as, hardness can be considered as, it is the degree to which, a molecular ion is easily distorted by interaction with other molecule or ion. So hardness is the degree to which the molecular ion is easily distorted when it interacts with other component, that is Lewis acid or Lewis base, which is either molecule or ion. And polarizability is dependent upon various other properties also. So if we see the hard species, which are, we have seen that these are hard species are small in size and compact, means the mass of that species, that is, we can say the nuclear charge as well as the electrons are packed in very small space, then it is harder species. If we consider H plus, Li plus, or any alkali metal, alkaline earth metal, etc., the atomic size or atomic structure is highly compact, therefore it is hard species. And if we consider the hard base, then, or hard soft acid or soft acid, then the size is larger. You can compare the size. So this is small size increases in this direction. So small size means greater hardness. Size is relatively increased, hardness is relatively increased. So with increase in size, the hardness goes on decreasing. Or in other words, we can say softness goes on increasing. So here, the hard species are not easily polarizable. These are called non-polarizable species. And soft species are larger in size and they are readily polarizable. So we can consider the cations with positive charge, means higher positive charge. If we see the oxidation state of the metal ion, generally you will find that the metal ions with higher charge, like +3 or more, +4, etc., they are mostly harder species. and if the oxidation state of metal ion is smaller, then these are softer species. So on this basis of charge or oxidation state, we can say whether it is harder or softer. Generally, we have seen that alkali metals, alkaline earth metals are smaller in size, more compact, and therefore they are harder species. Whereas transition metals of latter size, means towards right side in the periodic table, they are softer species because they are larger in size. They are having a small oxidation state and they are having pi electrons in order to form pi bonds with Lewis acids. So in this way, we can compare the hardness and softness, and on that basis we can explain whether the resulting species is stable or not, whether it is more soluble or less soluble. In other words, we can say if the substance or if the molecule or compound or salt is more soluble in water, then it is preferably the harder combination. And if the species or if the complex or salt is not soluble or less soluble in water, it has combination of either hard soft or soft hard type or soft soft type, then we can say it is less soluble. So solubility is another component. or in other words, we can say melting points or boiling points. Melting points and boiling points of hard combination is very high. Melting points and boiling points of species or complexes containing soft combination is much lower as compared to that with hard combination. So in this way we can interact or we can show the various interactions between such hard and soft Lewis acids and bases. So now we will stop our discussion here, and next time we will see how these metal ions are classified into hard and soft Lewis acids and Lewis bases, and how they can interact with each other to explain their various types of behaviors and applications of these hard iron and soft theory. So till then, goodbye, see you next time. Please subscribe to this channel and press bell icon and like button also. Thank you very much for watching this video.